Electric vehicle sales are growing fast. Over 20 million EVs were sold worldwide in 2025, a new record. That means 1 in 4 new cars sold globally is now electric, and reading those numbers, it might sound like the transition is nearly complete. But new car sales measure what's entering the market, not what's already on the road, and cars last a long time. In the United States, the average vehicle stays in service for over 12 years, so when you zoom out and look at the full global fleet, every car actually driving on the road, electric vehicles make up roughly 4%. After more than a decade of subsidies, mandates, and hundreds of billions in investment, 96 out of every 100 cars on the planet still burn fuel. The usual explanations for this are familiar: range anxiety, high prices, and charging inconvenience. The fact that EVs still struggle with towing, long-haul freight, or heavy-duty use. These problems are real, but they're not the core issue, they're symptoms. The real constraint on EV adoption isn't a single limitation, it's a system, a set of interlocking bottlenecks that all have to scale together, and right now they aren't. Start with coordination. The modern EV push didn't begin with consumers, it began with policy. Governments across the US, Europe, and China set aggressive targets, offered subsidies, and pushed automakers to accelerate electrification. And car makers responded rationally. They committed over $300 billion to EV platforms, battery plants, and factory retooling. Entire production strategies were redesigned around a future where electric vehicles would dominate new sales. But these systems move on different timelines. Policy can change in a year, consumer demand shifts over quarters, but industrial systems take years to build. And when those timelines fall out of sync, the system breaks. In the past 2 years, that's exactly what's happened. In the US and Europe, key incentives were adjusted or withdrawn, and regulatory targets softened under pressure from manufacturers. And consumer demand, particularly at current price points, has grown more slowly than expected. The result hasn't been a smooth transition, it's been a reset. Ford took a $19.5 billion write-down on its EV division. General Motors absorbed a $7.6 billion hit. For Stellantis, it was $26 billion. Collectively, the big three American automakers have taken over $50 billion in EV-related losses. Some have delayed production targets, others have shifted back towards hybrids and combustion vehicles to stabilize margins. This isn't simply a market correction, it's a coordination failure, where policy, industry, and consumer behavior moved out of alignment, and the system couldn't scale smoothly as a result. But even in a perfectly stable policy environment, the physical constraints would still be there, because electrification isn't just about cars, it's about materials, infrastructure, and energy. Every electric vehicle requires lithium, cobalt, nickel, graphite, and rare earth elements. And these supply chains are not only complex, they're highly concentrated. China refines around 70% of the world's critical minerals. For rare earths used in high-performance EV motors, it's over 90%. And for cathode precursors, a key stage of battery production, it's 95% or above. And this isn't a theoretical vulnerability. In 2025, China imposed export controls on rare earth elements, then expanded them to cover battery materials, cathode components, and manufacturing equipment. Automakers in the US and Europe struggled to source permanent magnets. Some cut production, prices in importing magnets surged. And diversifying away from that concentration isn't just expensive, it's slow. A new mine can take 10 to 15 years to move from discovery to production. Most exploration projects never reach commercial viability. And even when raw materials are available, the processing capacity, chemistry, infrastructure, and expertise often doesn't exist outside established supply chains. This can't be built overnight, and it can't be compressed into a policy cycle. Now add electricity, because even if you had unlimited vehicles and unlimited batteries, they still need power. And the grid is entering a period of rising demand it hasn't seen in decades. After nearly 2 decades of flat consumption, US electricity demand is projected to hit record levels in both 2025 and 2026. Data centers alone, which consumed about 4% of American electricity in 2023, are expected to reach somewhere between 7 and 12% by 2028, driven largely by AI. EVs, data centers, and industrial electrification are all competing in real time for the same generation capacity, the same grid connections, and the same infrastructure. But even if you solved all of that, the system would still hit another limit: everything in between. Transformers, the equipment that steps voltage up and down across the grid, are now in chronic shortage. Lead times for large units can exceed 2 years, in some cases closer to 4. Prices have roughly doubled since 2022. One charger installer described the situation simply: you can install the charger in months, but you might wait years for the transformer that allows it to connect. And these aren't mass-produced components. They require specialized materials, skilled labor, and custom engineering. Scaling them is slow. Rebuilding supply chains is slower. This is the part of the system most people never see, but it's often where the real bottleneck sits. And all of these constraints feed into something deeper, the feedback loops. EV adoption doesn't depend on one system scaling, it depends on all of them scaling together, and each one depends on the others. There aren't enough chargers, but there aren't enough EVs to justify building them. Manufacturers need scale to reduce costs, but consumers won't adopt at scale until prices fall. Utilities need demand certainty to invest in grid updates, but demand depends on adoption. And mining companies need long-term buyers, but buyers need stable supply before committing. Each of these is a loop, and they don't resolve independently, they reinforce each other. So instead of a smooth adoption curve, you get friction, repeated systemic friction, where progress slows not because the technology doesn't work, but because the system around it can't keep up. Take charging infrastructure. To support mass adoption, countries need vast networks of fast chargers, not just in cities, but across highways, rural areas, and logistics routes. In the US, there are currently around 218,000 public charging outlets for roughly 6.5 million EVs, a ratio of 30 vehicles per port. To meet federal targets for 2030, the country would need to install over 1 million more. But building chargers isn't the hard part, connecting them is. Every installation requires permitting, grid access, infrastructure upgrades, and often new transformers. Each step introduces delay. Each delay compounds, and at scale, those delays become structural. This isn't a question of whether chargers can be built, it's a question of whether the entire system required to support them can expand fast enough, consistently, across thousands of locations. And right now it can't. This is why the EV transition often feels like it's hitting the same wall, because in a sense it is. Not a single wall, but a system of constraints that keep reappearing at different points in the process. You solve range, and infrastructure becomes the problem. You expand infrastructure, and grid capacity becomes the problem. You build the grid, and materials become the constraint. Each layer reveals the next. And this is the key point. The technology works. Electric motors are efficient. Battery performance has improved dramatically. For many use cases, EVs are already viable, sometimes even superior. But the real problem was never really the car. It's everything around it. The grid that powers it, the materials that build it, the factories that produce it, the policies that shape it, and the infrastructure that connects it all together. These systems don't scale at the speed of software. They scale at the speed of concrete, copper, and coordination. So the EV transition isn't failing, but it isn't moving as smoothly or as quickly as expected. And in a system that depends on multiple layers, batteries, charging networks, energy infrastructure, and mining, all scaling together, speed matters. Because when those systems fall out of sync, progress doesn't stop, but it slows. And when it slows, the market adapts. Hybrids and other transitional technologies don't depend on the same infrastructure. They work within the system as it already exists today, not the system as it's expected to become. EVs aren't failing, they're just not moving fast enough. And in a system like this, speed isn't just important, it's everything.